Okay, we have seen a number of these probability distributions. Okay, discrete ones like binomial, like Poisson and geometric distribution, and for the continuous distribution like the normal distribution, like the exponential distribution, and of course we've got the chi-square and t distributions as well. Okay, later we'll get to use these ones, but just remember the most important of all is our normal distribution. Probably the name suggests this to you, normal. Okay, what's called normal. Yeah. The thing is, later when you get to do your experiments, okay, when you get to do experiments, what you will be doing is we collect samples. Okay, you're getting a number of experiment results or experiment data, so that you have a number of data with you, so that you have each one of them taken from your population. Okay, each one of them following these probability distributions. Just like when I throw my coin, each time I'm getting either a head or a tail, and when I repeat this n times, I'm getting a lot of heads and a lot of tails. Okay, so so one of the things we consider would be the mean value, or the sample mean, the mean value of your sample data. If you're going to collect any of these numbers from an experiment or whatever, one thing we would one of the first things that we would calculate would be the sample mean. Okay, but the thing is, because each of these numbers, x1, x2, x3, and all the way to xn, each one of them comes from your population probability distribution, so each of them being a random variable. So when you consider the sample mean, you just add them all up and divide by n. Okay, as a function of these random variables, it will be also a random variable. Yeah, so x bar is also a random variable, and therefore it will have its own probability distribution, just like the others. But the distribution, the probability for the sample mean, the probability distribution for the sample mean might not be the same as the axis. In fact, if what we know about this sample mean is that if you take a sample from a population, whatever, okay, eventually, when you have a large enough sample size, with a large enough sample size, the chance of x bar being close to the true mean value mu is going to increase. The chance that the x bar will be close to your true mean value mu will increase. Okay, this is what we call the law of large numbers. The law of large numbers. Okay, we're looking. We're if we're going to try to find the population mean and variance as we go on later in the chapters. Yeah. But the thing is, the only thing we could do is some experiments and collect some samples. So the best thing that our best guess would be our x bar. Okay, we have our sample mean. We're hoping that this sample mean would eventually look like the true mean value mu. But what should that be the case? This is what we call the law of large number here. What we have here is that the probability of your x bar being between mu minus epsilon and mu plus epsilon, okay, is going to be greater than or equal to this thing on the right hand side for any positive constant epsilon. What does that even mean? Okay, but what does that even mean? It means that the true population value mu here, which is never known. Okay, you don't know what that is. We're trying to estimate this number, but when we get our sample mean x bar, okay, we're just hoping it to be somewhere close. So we will say that x bar should roughly equal to mu, but this is not necessarily the case. We say that, sorry, for any value of for any uh, for any value of epsilon, no matter how small an epsilon, no matter how small an epsilon value you give me, I can say that mu minus epsilon and mu plus epsilon, that is the little gap around mu. There's a chance that my x bar, my experiment result would fall into this interval, fall into this little gap there. Of course, if the value of epsilon I pick is large, then more likely my x bar, my experiment result x bar would be between these two values. If the value of epsilon I pick is small, then it's less likely x bar would be in there. Okay, but the law of large number tells me that if you have a large number here, if you have a really large number, that is, if you have a large enough sample, when n is large enough, the sample mean will eventually be a good estimate to your mu because of this relation here. X bar would be the chance that x bar would fall between mu minus epsilon and mu plus epsilon would be greater than this number. What we say is, you see, there's 1 minus a little bit, so it's going to be less than 1, so it is good, nothing wrong with that. That's a perfectly nice probability here. Okay, but the thing is, it depends on a number of things. We said that if the epsilon we pick is small, if the epsilon we pick is small, then we're going to divide by something small here, epsilon squared, so it will be even smaller. So divide by something small, it will be a large number. 1 minus a large number, meaning it's going to be small. The probability of x being between mu minus epsilon and mu plus epsilon will be greater than or equal to a small number. So it's not very helpful if epsilon is small. Okay, how large a gap that you give me. But the thing is, the nice thing about this law here is that no matter for any positive value, epsilon here, no matter how small an epsilon you give me, no matter how narrow this gap here is, if we have a large enough sample size, we have n really large, eventually I will be dividing by a large number here. The second term here will be divided by a large number. So it will be like dividing by 100, like 1,000, dividing by something very large, meaning we're having a very small number taken away from 1. So the probability of this guy is going to be bigger than or equal to something really close to 1 anyway. So the probability of x being between mu minus epsilon and mu plus epsilon is going to be very large and close to 1. In fact, if you know anything about limits of functions when n like tends to infinity and all that, we can say that this probability approaches 1, is tending towards 1. It is almost certain, eventually when n is large enough, it's almost certain that x bar will be between mu minus epsilon and mu plus epsilon. Remember, no matter how small an epsilon you pick, no matter how narrow a little gap that you have to begin with, eventually x bar will fall between within this little gap there. Okay, that gives us this is a very important result here mathematically, telling us that there's a point in doing any experiment at all. Okay, it tells us that there's a point in doing experiment. There's no way we can tell what happens in the actual, the true nature, okay? Like what happens to my little coin, for instance. I don't know whether my coin will give me exactly zero point 0.5 of a chance of getting me ahead. Or why is it not 0.51? Or why is it not zero point 0.6? I never know. All I could do is do some experiment and then keep, and you probably, or common sense will probably suggest to you that the more time that I throw my coin, the more likely I'm going to get some uh, some reliable results. Okay, it would be stupid if I would like to check whether my coin is fair. It'll be no good if I just throw it twice. And then when I get two heads and I say it's not fair, when I get one head and one tail, I say it's fair. That's no good. You would probably suggest me to throw this coin a number of times, 10, 20, 30, 50, 200, maybe 1,000 times. The more, the better. Yeah, agree? So this happens here. There's a point when doing our experiments. The sample data that we collected, the experiment results that we have, at the end of the day, does reflect, well, in some way, to some extent, does reflect what happened to the true nature, to the true probability distribution that we have about this mean value or standard deviation value and all that. Eventually, okay, if we have our experiment done with a proper sample size here, okay. But for the moment, yes, X bar, no matter what the probability distribution we started, the sample mean eventually would be very close to the true mean value that we would like to find. In fact, we can go one step further to the most important result of this entire course, the most important result of this entire course, or in statistics generally, the central limit theorem. We've been saying the normal distribution is so important, but why is it so important after all? Because everything eventually would behave just like normal distribution. Because normal distribution is seen everywhere. In particular, in this case, X bar. X bar. No, your population, your population distribution could be anything. Could be a binomial, could be an exponential, or could be normal, could be anything. But when you collect your experiment results, x1, x2, x3, all the way to xn, the sample mean, as we discussed, it has its own probability distribution. What is it then? It'll behave like normal distribution when the sample size is large enough. When we say large enough, probably 30 is good enough. Okay, we don't really have to go through infinity unless you're a mathematician. Okay, X bar would behave just like normal distribution. So anything that we've done with normal distribution would be enough for us to find the chance that X bar would be with the chance that where X bar should be. Okay, so that if I have a population and then we with mean mu and variance sigma square. Okay, a population with mean value of mu and variance sigma square. Remember, here's the same. There's one thing here in statistics. We use Greek letters. We use Greek letters for things to describe parameters for the population, like mu, like sigma square. These are the parameters for the population. We use Greek letters for them, and we never know them truly. Okay, we use X bar to represent our mean value. We use S to represent our sample standard deviation and all that. We use Roman letters for our sample results, while we use Greek letters for the true population ones. Okay, so suppose that we've got a population, whatever that is, The whole thing is the whole thing is so important because this result is true no matter what population we started. Okay, there are a number of probability distributions out there. We've shown you a few, the exponentials, the normal, etc. But there are a lot more out there. But no matter what population that we have, your x1, your x2, or x3, whatever they are from, the sample mean x bar eventually would behave just like normal. With normal distribution, so what? Okay, with a mean value of mu and variance of sigma square over n. Okay, with variance of mu with sigma square over n. That means what? That means if you have a large enough sample size, like a large n value here, okay, when you work out your sample mean x bar, there is a fairly good chance that it will be close to the mean value mu. In fact, if you do a number of these experiments, if you got a lot of these x bar here, like if you do one experiment, you're repeating this 30 times, so you've got an x bar with 30 numbers. So you repeat your experiment again, do another 30 times, you get another x bar value, and then you keep doing this a number of times. The average of your sample mean, so it's kind of tricky to say, is the mean of your sample mean. Okay, the average value of the sample mean. If you get a lot of, if you repeat your experiment a number of times, each one with a certain value of n, so like 30, 50 or something, you get a value of x bar each time. If you do a lot of them, okay, they will have a average value very close to mu. Okay. And what is more, we've got a variance value. We've got a variance value of x bar that decrease with your sample size. Very important here. We have got this variance of your x bar depending on the sample size, decreasing with your sample size. That means what? If you remember, we talked about this. If you have a normal distribution, it looks like this, a bell-shaped curve, etc. If you have and this variance tells you the spread of your distribution, how widely spread, how tall and thin this is. If you have a large enough sample size, this variance is going to be very small, and therefore you have a really tall and thin normal distribution. That means what? That means most likely you have everything concentrated in the middle. So you would not be very far away from the mean value mu. You will not be very far away from the middle, the average, the mu here, your x bar. When your sample size is large enough, most likely x bar would be very close to the center, to the middle, to the mu here. Compared to if you have a small sample size, even though it might still be like a normal distribution looking like this, but your x bar is likely to be everywhere. Okay, so this is what happens. Very important here. Central limit theorem. X bar. Okay, your x bar, your sample mean would behave like a normal distribution. Okay, people often get confused. Of course, students very often confused with when do we have sigma square? When do we have sigma square over n? Okay, remember this is how you remember this. Yeah, for normal distribution, we have the mean value, we have the variance value, but this one, sigma square over n, is the variance value for your x bar, not x. The x comes from whatever probability distribution from whatever population you have there. It may be normal. It could also be a normal distribution. If x1, x2, x3, all the way to xn, they might come from a normal distribution. So we have mu, we have sigma square. But x bar, the sample mean, that is the one that comes with a variance of sigma square over n. Very important. difference here, which we shall come back to this in a bit here. Okay, so let's just give you, let me just give you a quick example to see what this all means. Okay, what do we use with what do we do with them? So here's the thing: suppose that we've got a vending machine selling soft drinks. Okay, so so when you put in your money in it, to just give you a little paper cup, and it just liquid comes out from the machine, and then you got your drink. Okay, of course, these things each time it will give you it should give you a fixed amount of liquid. So in this case, suppose that it comes in 200 milliliters, 200 milliliters. Okay, a little cup of paper cup of whatever, orange juice or coffee, whatever. Okay, but of course you know that these machines, they're just like everything in our real world, is never perfect. You're never going to get 200 exactly every single time. So that these machines, they come with the manufacturer, they'll give their the manufacturer will give these things out saying that this machine would come on average, okay, on average, with the setting here, it will give you on average 200 milliliters, sorry, 200 milliliters. But with a variance, or actually should be giving you a standard deviation, okay, a standard deviation of 15. So that we have mu equals 200 and standard deviation of 15. So if you like, the variance is 15 square. Okay, I'm too lazy for that, but it's actually 225 if you like. That's what the manufacturer claims that these machines would do. On average, it'll give you 200. But if you want to check whether these numbers are accurate, so you would go along and do an experiment. What do? You get a number of drinks from these machines and see if they really give you an average of 200 each time. Okay, it is unlikely that it will give you 200, 200, 200 every single time. But suppose that you got 36 of them. You do an experiment, so you're not going to just get 2 cups of drinks here. You got 36 of them. What is the probability that you will have an average of at least 204? If n equals to 36, what is the chance that x bar would be greater than or equal to 204? This is what we're asking. Okay, what is the probability that the average amount dispensed from these machines in a random sample size 36 is at least 204. By the way, we use the term random here. Okay, you see these things, this is something not exactly to do with the maths. Okay, for the maths we just take numbers and we just do the calculation, but in reality we have, when we do statistics, we have to consider other things more than maths. Okay, random sample. Suppose that that is how you collect your samples, how you're going to perform the experiment, how you're going to get these numbers. Okay, how you're going to buy these drinks? Are you going to buy them all at the same time, and you're going to put a machine there? Maybe this machine works better, I don't know, in the middle of the day or at different times of the day, where the voltage may be more stable, etc. You never know. Okay, so you don't know whether these things would work properly at every time. So if you're so you might want to do this at different times of the day, or when the machine is full of drinks to sell, or just when it may have very little left over. So maybe these things all affect the amount that will come out eventually. So random sample, it means how you're going to treat these things fairly. Okay, you're not going to just go along and just get 36 drinks for everyone in the class and then just expect this to be definitely reliable. Okay, you have to think about other factors, what may happen to your machines, how you're going to collect your experiment results, your sample. That would give you the most unbiased conclusion. Okay, but here's the thing: suppose that you're gonna doing this experiment properly, so you're getting 36 strings, you get your the amount measured. Okay, the amount of strings measured. So what is the probability that the average of them would be more than 204? Remember, if you're the manufacturer of these things, if you just whatever institute that you bought this vending machine to sell drinks to people, if on average this machine is giving more drinks, giving more liquid to people, you're losing money. Okay, so it's important to have these things quality checked, quality control. You have to check these things if they're performing properly. Okay. So to see whether this machine would behave as the manufacturer claims, on average 200, but what is the chance that you'll get 204 at least? Okay. When n is small, you can think of this. Well, again, we're not doing the calculations yet, but you can think if n is small, if n is not a large enough sample size, these numbers can be any number. You see. So it is likely the X bar could be any number. So it is more likely that you will get stupid numbers like 204, 210, etc. But if you have a large sample size, eventually everything would behave like what it should be. Okay, each of the x's can still be everywhere, but they should balance out. They should have the average out, and so that you have the sample mean value very close back to the middle, back to the where it should be, the 200, or if that is indeed accurate. So we have this here. Probability. What we know here is x bar behaves like normal with a mean value just like the one before. Okay, this time the x behaves like normal as well, but it doesn't matter. Whether x is like normal or what, but x bar behaves like normal as well. So with a mean value of 200, but with a variance value of 15 squared divided by 36. Okay, this is your sigma square over n. This is your variance for your x bar, not x, but x bar. So that we've got some normal distribution thing here, which if you remember, how we're going to find the probability of x bar bigger than or equal to 204. This is the same as saying probability of x bar less than or equal to 204, or actually just less than. But it doesn't matter. 204 with 1 minus it. Okay? It's like 1 minus the probability of x bar less than 204. Why do we do that? Because these tables, if we're going to use Excel or we're going to use these normal distribution tables for these calculations, it gives us probability to the left less than these numbers, not greater than. So we're going to do this x bar less than 204, and then we'll do what? And we have to change the variable to z. Okay, we're changing the variable to z. We're not going to find the probability for normal distribution with just these parameters, 215 squared over 36. We change that to z. That is, we have 204 minus 200 divided by, okay, your x minus your mean, the mu there, divided by sigma. That is your standard deviation, 15 over 6. Okay. We've got this is your variance for your x bar, and therefore the standard deviation will be sigma over n, sigma over square root of n. That is 15. over square root of 36, which is 15 over 6. Okay? Yeah, the 3's got cancelled, but I don't care. 2.5, I suppose. That is 1 minus probability of z less than, so this is 6 to 2.5, 2.5, and a 4. That's what? 2.4 divided by 2.5, that is sorry, 1.6. Yeah. So you just look up the numbers from this normal distribution table. Okay. Let's see, have I got one here? Sorry, I should have these tables ready before we. You see the normal distribution table, I've got 1.6, so I've got 1. No, I don't know if you can see this is 1.60 here. 0.5452 if you can read from these tables. 0.59452. Okay, yeah, that's probably, yeah, 9452. So I've got this here. The probability of getting z less than 1.6 is 0.9452. So the 1 minus that would be the rest, that is 0.0548. Okay, the chance of having your mean value, the sample mean value from 36 to be greater than or equal to 204 milliliters would be around 5%, 5.5% in fact. Okay, it's not something very likely to happen. 5.5% to have X bar greater than or equal to 204. Okay, so two things. Okay, one thing is, if you have a smaller sample size, this number will be higher. It's more likely that you would get your sample mean to be other numbers, to be any higher numbers. Okay, because each of these x's can be anything. But if you get a large number of these x's coming together, there will be a number a lot more than 200, but there should be numbers a lot less than 200 as well. So they got balance out when you can find the average. It's more likely you end up with something settled down to the middle. Okay, the larger the sample size, the less likely you will have something very different from 200, like 204 or more. Okay, so 36 here, the sample size of 36, the chance of having X bar less than equal, greater than or equal to 204 will be just like 5.5%. Not unlikely to happen. Okay, so the second thing is, what if it actually happens? If you actually do this experiment checking with these machines, we've just calculated the probability of having a sample mean to be 204, at least to be 5.5%. What if you end up, when you finish experiment, you have your sample mean value of 206? That means what? It will be so unlikely, or according to our calculation, it will be an event so unlikely to happen that maybe we should question about the claim from the manufacturer instead. Maybe there's something wrong with the 200 in the first place. Maybe there's something wrong with these machines. It's not working properly. Or maybe the manufacturer is lying to us. These things are giving out machines, giving out drinks and 200 milliliters each time. Maybe there's something wrong with these numbers. Okay, that's what happens to hypothesis testing. That's what happens in our next topic here. Okay, the thing is, as we said, we've got some population with some probability distribution that we will never know. Okay, there's nothing we can do about this. We don't understand nature after all, and there's no way we can determine these numbers precisely. Okay, these parameters, such as the mu, such as sigma square, and etc., or probability, just like my coin, we can only estimate them. Okay, but are we good at, how do we know that our estimate is good? Okay, or good enough? Okay, inferential statistics is what is it about? Okay, sometimes it's just uh, too difficult or too expensive to do this precisely. So imagine if I am again doing a study of exam result of a, I don't know, a class of 30 students, 50 students. All I need to do is, after the exam, I've got all the results, and now I only need an Excel file to have everything calculated in front of me, the mean value, the standard deviation, and all that. I've got everyone's result in my hand, then I don't need to do any estimates. But suppose we have a whole country. Okay, we're talking about the exam result of some of students. I don't know, across the country. We're talking about tens of thousands of students. Okay, I would like to compare their results, and I don't have enough resource here. I don't have all the information. I can only, and especially I'm only doing this on my own. I'm doing this by myself. I'm just one person. I can't possibly investigate all of the data. So I can only pick some samples. Maybe I'll just pick 30 again, or 50 from the whole from the whole lot, from the whole countries, 50,000 students. Okay, we just pick some sample. We're hoping that this would reflect the truth. Okay, too difficult or too expensive, require too much resources to do the study completely. You see, and that's why we will have to do estimates instead. Okay, use a sample results to see if it will reflect what happened in the truth. But sometimes it's simply impossible. Sometimes it's simply impossible to collect all the information. Imagine I've got my coin here. I've got my coin here. I would like to know whether my coin is fair, whether the chance of getting a head is exactly 0.5. What do I do? Throw this 10 times? Not good enough. 20 times? Maybe not good enough. 100 times? It may still not be good enough. In principle, I need to throw this coin forever and ever. Okay? We're not talking about 30 years. Okay, we'll have to keep throwing this until the end of the time. Okay, not me, pass it on to my children and children's children, etc. Forever, keep throwing this, keep collecting all these results until infinity. Okay, otherwise there's no way we can tell this probability precisely. Okay, if I throw this 10,000 times, even if I throw this 10,000 times, if I'm getting like exactly 5,000 heads and 5,000 tails, can you still say the probability of getting a head has to be 0.5? Is there any is it really not possible to have the probability equals to 0.501? You never know. There's no way you can tell. That's the thing. It's impossible to collect all the information. Okay, so again, we just have to estimate. I would, at the end of the day, we just have to be uh, have to settle. Well, we have to stop somewhere. We can't spend the rest of my life throwing my silly coin. I can only use like 300 throws or 500 throws of my coins to check my results and see how likely is it for my coin to be fair, how likely is it that my assumption, my hypothesis that my coin is fair to be true. Okay, that's what it would be. It was that was done instead of working out precisely the probability. There's no way we can do that. Okay. So here's the thing. Well, of course, if you want something more practical, it will be what is the success rate of a new drug in the market? How do you know? How do you tell that if you have a new drug or vaccine if you are doing COVID-19? Okay, what do we know about success rate? Okay, how do we know that? How do we do the true one? There's no way we can know the true number. Okay, there's no way we can check out all 7.5 billion people in the whole world and to see what the truth actually is. Okay, we're going to only find a few hundred people or thousands of people to check this vaccine or drug or whatever. Okay, and hoping these probably should reflect the reality. Okay, but at the end of the day, if we were to do anything, estimate, if we're doing any approximations at all, there's always a question how accurate this is. Are we likely to get something reliable? Are we likely to get something that reflects the truth? Or are we just having something stupid? Okay? That's what happens with this is what we have to consider in hypothesis testings. Okay? How are we going to perform an experiment? What are we going to collect? And how do we draw our conclusions from our experiment results? Okay? So let's just stop here for a moment. We can continue in a bit.